Welcome back. So, in the last class we looked at how chemical shifts arise, what are the different factors which affects the chemical shift values such as inductive effect, mesomeric effect, hydrogen bond effect and so on. In this class today we will look at another very important parameter in NMR which is called as J coupling. So, the J coupling has a very rich history and what basically was observed early on is that when you record an NMR spectrum for let us say ethanol, let us say to the more ethanol CH3 CH2 OH, what happens is CH3 we saw in the last class that it is 3 protons, they act as are chemically equivalent. So, they act as a single entity. So, CH3 you expect one peak, for CH2 the hydrogens of CH2 you expect another peak because both the hydrogens are chemically equivalent, and for the OH group, the H hydrogen attached to the OH, there also you expect one particular peak. So, basically in a ethanol spectrum if I record, theoretically or logically you expect 3 peaks in the spectrum. However, what we actually see in the spectrum is not 3, but some many peaks more. Basically what happens is each of the peak is split into smaller peaks, and this is why this is what was seen early on in the NMR spectrum, and it was it took a long time to understand what from where this originates, and there was then it was understood that this is because of interaction between two nucleus, nearby nucleus, for example 2 hydrogens mediated means carried out through the intermediate electrons in the bond. So, this is the basic origin. We will look at more detailed aspects of the J coupling as we move on. So, if you look at this spectrum here, you can see here this is what is shown, what is meant by the multiplet structure. So, you can see each of this peak here is not a single peak, it is split into smaller peaks. So, this for example looks like a triplet, means 3 peaks. Here it looks like more complicated peak structure, and similarly here you can see there are many peaks which are within this particular peak envelope. You can see in a similar manner here that there are multiple peaks here. So, this is what was very intriguing in the beginning of NMR spectroscopy, and this was then discovered that this is because of what is called a J coupling. So, what is J coupling? J coupling basically is the interaction between 2 spins, and therefore, we also use the word spin-spin interaction. So, it is interaction between 2 spins. We will look at theoretically from where does it come, and because of this interaction the peaks of each of the spins is resolved or split into more lines. So, J coupling is also known by the word scalar coupling or through bond interaction and so on, and like chemical shift, J coupling also does not change with change in the magnetic field. So, for example, if I measure the J coupling of between 2 atoms as at 300 megahertz spectrometer as let us say 10 hertz, that value will be the same if I go to higher magnetic field. So, that value does not depend on the magnetic field. So, let us now look at the theoretically from where does this J coupling come about. So, I will take an example of 2 hydrogen atoms. So, we will call it H A and H B. Okay. So, now this hydrogen atom can exist in 2 spin states which we saw alpha beta. Similarly, this hydrogen can exist in 2 states alpha beta. Now, if there is an interaction between these 2 spins, then what happens is we consider this whole thing as one spin system. We do not consider the 2 spins separately, we call this together as a one spin system. So, we can write the now because there are 2 spin system. Now, there are H A has energy levels alpha beta, similarly H B has energy levels alpha beta, but we do not consider now this as separate. We will combine these two, and this results in 4 energy levels. We can call it as alpha alpha, alpha beta, beta alpha and beta beta. So, we can say this particular the first letter the alpha state correspond to H A and the second will be H B. That means, if you look at this particular transition, what is happening is the H alpha, the alpha state of hydrogen is same, of H A is same, but the beta is undergoing from alpha to beta. So, this is a transition corresponding to H beta. Similarly, if you look at this particular transition, that is molecules when they get excited from this energy level to this energy level, again the H A is constant, it is both beta state, but the H B is going from alpha to beta. So, therefore, this particular transition also corresponds to H beta. So, this is basically this whole drawing which is shown here, this particular this is one particular system and there are 4 energy levels now, because there are 2 alpha beta for each, and therefore, 2 into 2 makes it 4 energy levels for a spin system which contains 2 hydrogen atoms. Now, this particular energy transition from this energy level to this energy level now will corresponds to A, because in this particular case alpha of A is changing to beta, but alpha of B is remains alpha. Similarly, if you go from here to here, this corresponds to transition for A, because the hydrogen atom A is going from alpha to beta, but the hydrogen atom of B remains in the beta state. So, this is the particular scenario when we say that these two together form a spin system, that is a combined system. However, now suppose there is a J coupling between the two. So, let us say now that there is a J coupling between the two. Because of this J coupling, this whole picture now changes. What happens is, we say that the energy at any for any given spin system, energy is equal to E A plus E B. This is the total energy of the system if you consider A hydrogen and B. But in case of J coupling, we have to add one more term which we write it as M1 M2 J, where J is the J coupling value between the two atoms. Now, if you take M1, so these are basically the spin states, these are the spin states. Okay. So, now if M1 can be equal to half, it can be M1 can be equal to half or it can be minus half. M2 can be equal to half or it can be minus half. So, there are 4 possibilities: half half combination, half minus half combination, minus half combination, and minus half plus half. So, this is what is shown here. Here it is half half, in this particular case it is minus half plus half, and in this case it is minus half, and this is case it is plus half minus half. So, the 4 different possibilities, 4 different the spin states are captured in this particular diagram, but now the energy levels will also start changing. What happens is, if you look at this picture this side, what will happen is this particular energy level, if I draw a line here and look at this energy level, if I draw a line here, now what happens, this is E A plus E B now plus M1 M2 J, but M1 and M2 both of them are plus half, and therefore, this total adds up a value J by 4, half into J. So, this basically becomes E A plus E B plus 1 by 4 J. So, what basically is happening is, this particular energy energy value, where you can see the red dot here, this particular down below. So, let me so if you look at this particular here, so where the pointer is, you can see this energy level, which is a ground state energy level. This is another excited state and this is also excited state. Now, you can see the energy levels of these states are modified because of an additional term which is shown here. So, you can see because of this M1 into M2 J, which is adding to the total energy, based on what is the value of M1 and M2, the energy level starts changing. So, now these energy levels is shown here. Earlier it was in the absence of J coupling, but because of the J coupling, now the energy levels of these states starts changing, and it basically what happens is, you introduce extra energy. So, we will see that in this next slide. So, we can see here particularly in this particular slide. So, we can see that suppose I draw a 2 energy level here. Now, what happens is, this energy gap is now E A plus E B plus 1 by 4 J, because M1 into M2 makes it 1 by 4. Now, this one is E A minus E B minus 1 by 4 J, and this is E A minus E A plus E B minus 1 by 4 J, and this one is basically E A plus E B plus 1 by 4 J. So, what has happened if you now look at the transition, this transition which was corresponding to H beta, H b, this is alpha alpha, this is alpha beta, this is beta beta, and this is beta alpha. So, this one which we saw in the previous case, that this corresponds to the transition of H b. In this particular case, the energy is now earlier the energy value of this, you can see this minus this, there is a additional contribution of plus 1 by 4 j. So, if you add these two, basically what has happened is these two energy levels. Now, if you look at this transition here, this is another transition corresponding to again H beta, because H alpha is constant, H beta is taking a change transition, and because of this what happens is the two energy levels. Now, if you look at this difference here, this minus this, what has happened is it has, because of this additional term, it has gone down by minus 1 by 4 j, this minus this. Similarly, if you look at alpha alpha minus alpha beta, what has happened, it has gone up by 1 by 2 j. So, basically if you look at the H beta peak, it has got split into 2 now. This is the original H beta peak where it should have come, but because of this splitting, it has become 1 by 2 j, 1 by 4 j this side, 1 by 2 j this side, 1 by 2 j this side, and the total difference has become j. So, because of this presence, because of the presence of the j coupling, so because of the presence of the j coupling between H beta and H a, the H beta peaks now get split into 2 peaks. It no longer becomes, is no longer as a single peak, it has got split into 2 peaks because of this change in the energy of the transition. And where is this energy of transition change coming from? It is coming because of this term here, that each of this term adds some energy level to the lower state, subtracts some energy from the upper state. So, because of these two energy levels have come closer by 1 by 2 j, and these two levels have gone further away because of 1 by 2 j. So, therefore, this is how we can explain that these two transitions earlier they were of the same energy level. So, they were one peak. Now, because of this addition of j coupling value, it has got split into 2 different peaks. The same situation will happen for A. In the case of A, your peak will now be not one single peak, it will got split into 2 because of this transition here. Now, it has got minus 1 by 2 j this side, and here it is plus 1 by 2 j this side. So, compared to the earlier scenario, it gets split into 2, one goes to plus 1 by 2 j minus 1 by 2 j this side, another goes to plus 1 by 2 j this side, and the total difference becomes j. So, H a has got split into 2, H b also has got split into 2. So, this is basically the explanation of how the j coupling comes from. J coupling comes basically because of this situation, that the energy levels of A, which was earlier a single peak, because of there is no coupling, because of the presence of coupling with another spin B, it gets split into 2 halves, and this is exactly the half, in the sense initially if the signal was 100% here, it becomes 50-50. So, the whole signal has come down by 50% and split into 2 peaks instead of 1 peak. So, this is called a multiplet, it is called a doublet in this particular case. Similarly, here in the case of H b, it has also got split into 2 and it has become a doublet. So, this is how j coupling comes about. So, one important thing to understand is j coupling is, now you can see if H a splits H beta into 2 peaks, H beta is also splitting H alpha H a into 2 peaks. So, you can see that both the hydrogens they split each other. So, this is a very important point to keep in mind, that when one spin splits the other peak into 2 because of j, the other peak also splits the original one into 2. So, it is a mutual, equal and opposite kind of effect. And if you see one more thing, this j value is a measure of the coupling. If j is very high, we say the coupling is good. If the j is very low, we say the coupling is very weak. So, therefore, this j value is the strength of the coupling. It depends on the strength of the coupling, and therefore, it matters whether it is a heteronuclear coupling, it will be different hydrogen coupling, hydrogen proton coupling and so on. Now, if you can extend this picture more, let us say that we take a molecule which is shown here, that I have one hydrogen on one side, but now I have 2 hydrogens here. So, instead of H alpha, let us say this is H a, this is H b, but here there are 2 H b's, there are 2 equivalent H b's. So, then it is not similar to this picture, because this picture was only for one hydrogen atom interacting with another hydrogen, but here one hydrogen atom which is shown in the yellow shade is now interacting with 2 hydrogen atoms. So, this is through bond coupling. So, remember J coupling is always through bond, which means that these 3 bonds, this hydrogen is shown in this yellow shade is now interacting with this hydrogen via 1, 2 and 3 bonds. Similarly, this hydrogen is interacting with this hydrogen here also via 1, 2 and 3 bonds. Now, let us suppose, this is an assumption now, let us suppose that these 2 hydrogens are equivalent. Please remember, this is not always the case. It is not always possible to say that the 2 hydrogens like this are chemically equivalent. They may be chemically equivalent or they may not be chemically equivalent. Therefore, it is very important not to assume things, but let us say for this particular example that these 2 hydrogens are equivalent. Then we have a very famous rule known as the n+1 rule, which is shown written here. It says that if a given nucleus, there is hydrogen example in this yellow color, is attached to n other nuclei with the same J coupling value, means suppose this hydrogen is having a J coupling with this hydrogen, that value let us say is some J x value, and if the same x value is for this coupling, then this particular yellow color hydrogen shown in yellow color shade will be split into 3 peaks, because it has 2 neighbors. So, whenever there are n neighbors, then there is called n+1 rule. This n+1 rule, remember, applies very specifically only to a particular case. And what is that particular case and condition which should be satisfied? Number 1, it should be coupling to the same hydrogen, I mean it should be having the same value to 2 different hydrogen. These 2 different hydrogens may be chemically equivalent, may not be, need not be chemically equivalent. Okay. But the value of coupling of this hydrogen to this hydrogen and the value of coupling of this hydrogen to this hydrogen should be same. Typically this happens when these 2 hydrogens are chemically equivalent. So, this n+1 rule is very specifically applied only in the case where there are chemically equivalent hydrogens and an hydrogen atom is coupled equally to both these hydrogens. So, this is what is shown particularly here, that in this particular case the yellow color hydrogen gets split into 3 peaks because of 2 neighbors here. So, n+1 is equal to 3. So, this yellow color hydrogen, the hydrogen shown in yellow color shade will appear as a triplet. Now, triplet means what is a triplet? Is it 3 peaks and what is the relative intensity? We will see that in the coming next few slides. Look at this example here now. Here what is shown in this shade has 2 hydrogens, and now let us assume, as we saw here, that they are chemically equivalent. So, if they are chemically equivalent, then these 2 are considered as one entity or one hydrogen. Okay. So, now these 2 hydrogens considered together as one, okay, they are together as one. Now, these 2 together are coupled only to one hydrogen here. So, if you consider these 2 hydrogens as one unit, then this one unit is coupled by J coupling to another only one hydrogen. That means, this unit has one neighbor, and according to the n+1 rule, this unit together will be split into 2. So, because this unit is chemically equivalent unit, for us it is giving you, if there is no coupling, it will give me only one proton, means one peak, one type of proton, 2 protons, but both are equivalent. So, they will give me one peak, but now because they are coupled to this hydrogen, that peak will get split into 2, and that is called a doublet. So, doublet basically, as the word sounds, it is basically, it means 2 peaks, as the word sounds here, it means 3 peaks. So, like that we can actually look at the different types of coupling which is shown here in different examples. So, you can see here this particular hydrogen which is shown in this arrow and this particular hydrogen. Now, what happens is this x and y are not same. Suppose x and y are not same, which means that these 2 hydrogens are not equivalent. So, therefore, this hydrogen will split this hydrogen peak into 2, and this hydrogen will split this hydrogen peak into 2. This is what example we saw in the previous slide. If you have HA and HB, then each will split each other, and this is what is shown here, that both of them give a doublet peak. So, both the hydrogens are got split into 2 each. Now, consider this case where this CH3, remember according to chemical equivalence theory, these 3 hydrogens are equivalent and they will all be in the same peak. They will be one chemical shift value, they will all be equivalent, but these 3 now therefore, you should consider as one unit as far as chemical shift is concerned. So, therefore, this unit will be split by this hydrogen into a doublet. So, this is what is shown for a CH3. So, on the left hand side what you see here is a CH3 peak which has got split into 2 because of this hydrogen. Now, if you look at this side here, what is happening? This hydrogen is having 3 hydrogens as neighbor, but all the 3 are equivalent, it does not matter. As far as this hydrogen is concerned, it sees there are 3 hydrogen in its neighbor, therefore, and all the 3, because they are equivalent, it is having the same coupling to all of the 3 hydrogens, and therefore, this hydrogen will now get split into 4 peaks by the n+1 rule. So, the n+1 rule says that this hydrogen, which is I am indicating by the arrow, gets split because of this CH3 into 4. Now, look at this pattern here, it looks very strange pattern, but how does this pattern come? We will see in a few slides from now how this pattern can be derived mathematically. It is very easy to do that. But now, one thing we should not, you should ignore here, which I have not drawn properly, is the intensity. So, this is just as a schematic to show you the peak splitting pattern. Therefore, the intensities are not to scale, which means these 2 peaks you would expect 3 times bigger than this peak. Why? Because this is one hydrogen together and these 2 together are 3 hydrogens, CH3 CH. So, you expect this unit to be 3 times stronger than this, but for the sake of explanation I have ignored the intensity right now. You have to only focus your attention on the peak pattern. Now, look at this peak pattern here, this is CH2. So, we are assuming these 2 are chemically equivalent and therefore, these 2 together act as one unit, both of them are split by because of this hydrogen into 2, and that is the CH2 peak what you are seeing in this left side. And on the right side, this hydrogen now is coupled to both these equivalent protons. So, there are 2 protons here. So, n+1 2 means 3 peaks. So, this CH gets split into 3 peaks and this is the triplet peak. Again, how the intensity is in this manner we will see in the next few slides. Now, consider these 3 CH3 CH2. Now, here CH3 which is on the left side we get split because of the 2 into 3 peaks. That means, all the 3 hydrogen which are one entity, one unit because of chemical equivalence, now they get split into triplet because of 2 hydrogens which they are coupled to. This is what is on the left side. On the right side, these 2 hydrogens now are equivalent, but both of them are coupled to 3 hydrogens, 3 on this side. So, n+1 rule says they should get 4 peaks. So, this is what is similar in this case. So, whenever you have any CH or CH2 coupled to a 3s3, you will get a quartet. This is called a quartet. Quartet means 4 peaks. Now, we can extend this idea to the scenario here. Here you can see both are CH2 CH2. So, they will get split by each other into 3 peaks because n+1 is 2 + 1 and 3. So, both the CH2s now will show triplet each. And then finally, in this particular case, which is a more complicated structure, this is an isopropyl group, very common in amino acids, in chemistry and so on. So, very often you will encounter this kind of a moiety. So, here you can see there are 3 hydrogens, there are 3 hydrogens. Now, what happens is both are CH3, so both are further equivalent. So, what it means is that these 6 hydrogens together act as one unit. So, they are basically one unit. So, these 6 hydrogens are one unit and these 6 together are coupled now to one hydrogen. So, these 6 hydrogens which act as one single hydrogen because they are equivalent, they will show a doublet which is shown this side because of one single hydrogen. On the other hand, this side hydrogen, because now it is coupled to 6 hydrogens, it will become 7 peaks. So, you see this is how the n+1 rule 6 + 1 7. Again, remember intensity pattern we will see shortly, but the idea in this whole slide is to illustrate how this different splitting happens because of J couplings. Now, where does this splitting pattern come about? So, for that we will go like this. So, if you look at this, this is called as a Pascal triangle. It is a very famous way to obtain the chemical the peak coupling pattern. So, let us look at it like this. So, let us say there is no coupling. So, let us take a hypothetical nucleus A which has no coupling. So, when there is no coupling, it is obviously only one peak. Now, because of coupling to any other hydrogen, any other nucleus, Suppose let us say it has only one hydrogen in the neighbor. In that case it will get split into 2. This is the doublet. So, this is what is drawing here, drawn by this triangle, this 2 lines, and this is a doublet. Now, what is happening? Let us say that the intensity of this line, which is shown by, which I am pointing by this arrow, is 1, then because of the splitting it gets equally divided into half and half. So, you can see this is called 1:1 pattern, because the ratio of this to this peak is equal, they are both equal. So, 0.5:0.5 is 1:1. This is what happens when there is a J coupling to one nucleus. Now, I can take now J coupling to a second nucleus. So, imagine now a situation where we have something like, so we looked at this particular case is when H A is coupled to one another H B. Okay. So, this is basically 1:1. Now, consider another case where there is now one more. So, we can look at this particular case. So, there is one more HCH and there are 2 hydrogens. So, there is HA, HB, HB, 2 hydrogens. Now, what happens in such scenario? So, this is what we have to now look at. Now, because of this these 2 hydrogens here, what is shown here, these 2 hydrogens, this one gets first split because of this into 2. So, this is what you see here. Now, next this hydrogen you consider, and that will further split this hydrogen into another 2. So, first this peak is splitting, this HB is splitting HA into 2, then another HB is splitting this, that other 2 peaks into further 2 peaks. So, you get 2 into 2, 4 peaks. So, that is what is shown here. But what happens is, because the values are same, that means the J of HA to HB is same as HA to this HB, therefore, this J is same. So, the middle line when you draw a line from here and you draw a line from here, and the distance between these 2 is J, distance between these 2 is also J, then what happens is the middle lines, they collapse, they join together. So, when they join together, they add up in their intensity. Therefore, this peak, which is 0.5, got 0.25, 0.25 in the beginning. Similarly, this 0.5 got split into 0.25 and 0.25, but in the middle those 0.25 and 0.25 they add together and they become 0.5. So, therefore, after splitting because of these 2 hydrogen, this HA now has 3 peaks, 1, 2 which are together and 3. So, now what is the relative ratio of the intensity? It is 1, this 0.25 is 1, 0.5 is 2, 0.25 is 3. So, you can see in this manner that if you look at this, you have 0.25 and 0.5 and 0.25. Now, if you take a mathematical ratio, it is 1:2:1. So, this is how the triplet comes from, because of coupling of this hydrogen with these 2 hydrogens. Okay. Now, let us say that there is one more hydrogen here. So, there are 3 hydrogens. So, in that case the third hydrogen will also split this into 2. So, then each of these peaks will further get split into 2, then further it will be half of 0.25, and again because of the same J value coming repeating everywhere, the middle, there is one which comes from this side and one which comes from this side gets joined, and therefore, it adds up together. Similarly, here it will add up together. So, you see now if you draw a line like this, which is half of this 0.25, so 0.125, this side 0.125, but here also from 0.5, this is 0.5, remember. So, half of 0.5 is 0.25. So, 0.25 from this side, 0.125 from this side becomes 0.375. Similarly, the logic here, 0.25 contributes half of itself, that is 0.125, 0.5 contributes half, which is 0.25. So, together is 0.375, and this peak last one is half of 0.25 and it is 0.125. So, now if you take the relative ratio, it becomes 1:3:3:1, and that is the concept of a quartet. That is what is a quartet. So, you see in this manner one can keep on splitting this hydrogen because of any number of hydrogen around itself. So, if there is one more hydrogen, you can split it further. If you have one more hydrogen here, you can split it further, and what one has to do is start from initially with no splitting, then start splitting because of the hydrogen into 2 peaks, half and half, and give a, because of some J value, then further split because of the next j, and you can keep on doing this j value as long as you have. So, for example, if you go to the previous slide, when we saw here, this is what happens, that there is now a 6 peaks. So, here we saw this is a quadrate, just now we saw how a quadrate comes because of this hydrogen is split into 4, but now here this hydrogen is split into 7 because of the 6 hydrogens here. So, that pattern also can be derived using this J coupling, and I would suggest you as an exercise to work out that given another hydrogen and like this up to 6 hydrogens, how will this pattern look like and what will be the relative ratios. So, we will continue in the next class with J coupling, and we will see some more interesting features of J coupling, what are the typical values of J coupling, how they are useful in structure determination and so on.